Hi guys. So how do we use this O notation I just told you about in the previous video? Well, it allows us to get away from little details when measuring how fast algorithms are, or how much space they take up for that matter. Those are both things that people are very interested in. Okay? The one way is it's fairly clear that basically any linear function, all of them have the same asymptotic growth. Because if we have, say, slope times n plus intercept, and we take that and divide it by n, what we're going to get, okay, let's do this more mathematically. Okay, so we'll go take this whole thing, put it into math mode. Okay, and I'm going to put some parentheses around it. Slope times n plus intercept divided by n, and we want to take the limit. Okay, so we'll take, well, first of all, I can put this into math mode. Okay, divide by, a little confused, but get the basic idea. And this guy, I want the limit as n goes to infinity. Let's just copy. And of course, as you see, this thing gets confused, but I can make the math right. Okay, so we'll take this, n goes to infinity, and this guy is what we're taking the limit of. Okay, so it'll be that way. Now, this is fairly clearly, I'm sure, but let's just put that in. Turns into the limit. Oops. Get that. Sure. Oops, that's not where I want to go. Go away. Not that. Okay, this, I guess this is right. Turns into the limit of slope plus intercept over n. So we can turn this guy, this little piece of math, into just slope plus intercept divided by n. And that equals slope. Since as n goes to infinity, this part goes to 0. Which is, as you know, a constant. So, basically, any linear function is the same as n. And this means that all linear functions are O of n. Now, so this is going to be important. Okay. Similarly, all constant functions are O of 1. Yeah. And anyway, all, okay, so, and I'll leave that one up to you, but it's fairly clear. The limit of a constant is a constant. Now, that's what being constant is all about. It's not changing. So, the main thing here is, let's talk about a simple linked list. Okay, and let's talk about searching a linked list. We talked about that earlier in the previous class, so it shouldn't be too... Well, we talked about, in the review, we talked about deleting all the negative numbers from a linked list. Let's just talk about searching a linked list for a key. Okay, so we want to find a key in a linked list and then get its value, right? So let's say the linked list was a dictionary. We want to search for, we want to know the definition of the word, say, asymptotic. So if all our words are in linked list, we can search for the word asymptotic and see when we find it. Now, the best case is when the key is in the first link of the list. Okay, remember this is a linked list, so the only way to get the second one is to go through the first. The only way to get to the third is to go through the second, and so on. But when the key is the first link, it just takes... And the other thing is we're going to measure by how many key comparisons. So how many times do we compare our key that we're searching for to the keys in the list? Okay, so we're going to ignore the time it takes to compare two keys. Now, why can we get away with this? Because multiplying a constant by a constant still is O of 1. Multiplying a linear by a constant doesn't change it being linear. So, if our computer gets twice as fast, it doesn't change the O notation. If our algorithm for comparing takes a bit longer, it doesn't change the O notation. This might be modified, and I'll talk a little more about that in future classes. But basically, we're going to just count key comparisons now. So, when it's the first link in the list, we've done... So in the best case, it's one comparison, or O of 1. Very simple. Now in the worst case, how many comparisons? Well, we've got to, in the worst case, it's at the very end of the list, or not in the list at all. So in the worst case, we need to look at all the keys. It's the only way to do it. And so in that case, we have, so the worst case needs n comparisons, which makes it O of n, the size of the list. Now the average case is more complicated because we need to know how often we succeed in finding the key and how often we fail. So let's create two new symbols. We'll have P of success will be probability that key is in the list. And this is going to come up over and over again with our data structure. So the probability the key is in the data structure, we're going to turn that. In this case, it's a list. And I bet you could figure out for yourself what P of failure is. But I'll write it down anyway. Probability that key is not in the data structures. Now, since everything happens, since you'll either succeed or fail with a probability 1, P of success, and you never do both at the same time, plus P of, let's type this right, P of failure equals 1. So what we need is something like a weighted average now. Okay, we'll also assume another assumption. Now we need an assumption. We're going to assume that the key is equally likely to occur anywhere in the list. Now that's not necessarily true. It might be that we rearrange the list to move the more likely keys to the front or something. But we're going to assume right now we don't know that. So in this case, the average number of comparisons we need when it's successful will be, so when successful, the number of comparisons will be the average of the best case and the worst case. Now that's not always true, but in this case where everything is distributed equally, it will be true. So it'll be, let me put that in math, 1 plus n over 2. And we discussed before, the failure, when we fail, we always got to look through the whole list because we don't know we're going to fail. So the average case for searching, and I'm not going to use O notation, although it's important. Searching a list, I'll talk about the O notation in a second, will be probability of success times one plus n over 2. Close enough. Plus the probability of failure times n. Now there's different ways to algebraically rearrange it, but it's clear this is a linear function. So this is going to be, if we want to be strictly mathematical, oh, oops, I turned off. I want it to stay on. Okay, let's try that again. We want to keep this strictly mathematical. That we call that a member of O of n. I think I'll leave you to think about that a little bit. So, what I want you to consider, does this change when the list is sorted? Now this is going to relate directly to the projects. We're going to do projects 1 and projects 2. And And soon I'm going to assign you to that project with a due date. So, that's, I think, enough for you to think about right now.